In this tutorial, we're going to be finding the heat of formation of magnesium oxide using a calorimetry and then Hess's law. So this is the equation for the heat of formation of magnesium oxide. So if you have a magnesium solid, if when we burn that in the presence of an air, it makes a magnesium oxide. So what's going to be the delta H for this reaction? And that's what we're trying to figure out. And it's not that easy to figure out the delta H of magnesium oxide if you just burn the magnesium in the air. So instead of doing it that way, we use Hess's law, where we're going to be using these three equations and using the delta H's of those three equations to figure out what the delta H going to be for this target reaction. So this first reaction is going to be our target reaction. Okay, so we have the delta H for the third reaction where we have the H2 reacting with O2 and making water, so that's actually given to you. And the delta H for these first two reactions you have to experimentally find. And once you have the delta H's, delta H1 and delta H2 of those two reactions, we can manipulate those using Hess's law to get to our target reaction. So we'll worry about manipulating that in a bit, but let's worry about calculating this delta H1 and delta H2. So in first reaction, we're going to be dissolving or reacting our magnesium solid in hydrochloric acid, and then in the second reaction, we're going to be reacting our magnesium oxide in the hydrochloric, and then we're going to be trying to figure out how the heat is going to be changed there, whether it's going to be released or gained. That depends how the temperature is going to change. So let's focus on the first one. So let's look at this first reaction. So this is the normal setup for the calorimetry, and you guys are going to be using the foam cups in your labs, and you may use two foam cups just to kind of make a better insulator so that no heat is actually lost to the surroundings. So whatever heat is going to be released by the reaction, that stays inside the container, and you can measure the rise in the temperature or the drop in the temperature depending on whether it's exothermic or endothermic by using the thermometer that's already inserted into this calorimetry. And then you also have a stir there that you can use to stir the solution once you add your reactants in there. So one of your reactants for the first reaction is obviously going to be the magnesium. And let's suppose I'm using 0.5 grams of magnesium, and you might well be using a very different amount of magnesium, but I'm just gonna, for the sake of calculations and as an example, I'm just gonna use up some random numbers there. And the amount of HCl that I'm gonna be using for this particular reaction is gonna be 100 milliliters. Okay, so I have my HCl into this calorimetry cup, and then I need to have the initial temperature of the HCl as well. So once you put this HCl in the cup, you have to leave it there for about 5 minutes or so, just to kind of make sure that both the calorimetric cup and your HCl is in thermal equilibrium, and read the temperature, initial temperature. So let's say the TI, I'm just going to pick a room temperature. It's going to be about 22.0 degrees Celsius. And now, once you have found the initial temperature, you want to go ahead and add some magnesium in there. So when you drop the magnesium into the cup, so let's assume, let me change the color there maybe. So I got the magnesium in there. It could be very well a ribbon of magnesium, or maybe you could have the pieces depending on what kind of what you have available in your lab. And then you're going to start stirring it, and obviously what's going to happen, this magnesium, it will react with HCl according to the reaction that we have seen earlier. So we have magnesium solid, and it'll start reacting with HCl, and it makes magnesium chloride plus H2. And then in the process, it actually an exothermic reaction, so it's going to release the heat. So make sure you balance this reaction. So it's going to have two there, and that should take care of it. It's going to it's going to release the heat. So if it's an exothermic reaction, what's going to happen to the temperature? So over time, you're going to have an eye on your thermometers and see how the temperature changes until you get the highest temperature. So let's say your temperature went all the way up to, well, I'm just going to make up some number there. So let's assume it went all the way up to 45 zero point zero degrees Celsius. Okay, and after that it didn't go up or it starts coming back down. So you want to actually read the highest temperature you can possibly have there. So that's pretty much you have for this reaction one, and these are the values you're going to be looking for. You make sure you know the mass of magnesium, you make sure you know the HCl, the amount of HCl you're using, and then the initial and final temperature you're going to be reading from the thermometer. Now, what actually happened here? So when the reaction took place between the magnesium and the HCl, it was actually an exothermic reaction, so it released the heat. So the heat released, all right, so I'll say heat lost by the reaction is going to be equal to the heat gained by water. And I can probably say the calorimetric cup. Okay, so since it's heat lost, I can just put a negative sign there. Now again, a negative sign just means you're losing the heat, but at the end of the day, what's more important to know is this particular reaction is actually an exothermic reaction. So if you have an exothermic reaction and when you find your delta H, it's going to come out to be a negative number. So how do you find the heat gained by water in the foam cup? So your heat gained by water is going to be the mass of the water or the mass of this reaction solution, which is going to be the MC delta T. So it's going to be the specific heat capacity for the water and times the delta T, which is change in temperature, plus the heat gained by the foam cup, which is going to be the calorimetric constant C times the delta T. Now, I didn't mention that earlier, but this HCl solution, you're going to be treating this just like you treat water for the sake of keeping things simple. For example, the density, you're going to assume it's 1 grams per milliliters, and the specific heat capacity of this HCl solution will be taken as just the specific heat capacity of the water. So that's why I said here the heat gained by this reaction solution or the water. Okay, so then how much mass we got in there? Okay, so the mass of the solution, so initially we had 100 milliliters of HCl, which is roughly going to be 100 grams as well, because the density of the solution is going to be 1. And if you want, you can say I have added 0.5 grams of magnesium, so you can add that 0.5 into the 100 so that you are consistent with your mass. So it's going to be 100.5 grams as your mass times the specific heat capacity of water is going to be 4.184 joules over grams degrees Celsius, and then your change in temperature. So your final temperature was 45 minus your initial temperature is 22 degrees Celsius. Okay, so that's your MC delta T. Now, as far as your C delta T go, the heat capacity for the calorimetry, a lot of time it's going to be assumed it's 0. What that really means is the foam cup doesn't really absorb any heat. So it's a perfect insulator, so all the heat that's going to be released by the reaction stays inside the reaction solution, or the water in this case. So for the most part, this C delta T is not going to be even taken into account. And in that case, you just ignore it. But then suppose you do take that into account, and if you do take that into account, you have to have this value of C. And a lot of time you actually find the value of C before you actually start doing this experiment. So I do have another session, another video posted on how you're going to be using this in the calculations if you do happen to have the value of heat capacity. But for this one, we're just going to ignore it, assuming it's a perfect insulator and no heat is lost to the foam cup and to the surroundings, obviously. So this whole term becomes 0, so only worry about the MC delta T. Okay, so let's go ahead and figure out what that's going to be now. So we got 100 times All right, so let's do this 100.5 times 4.184 times 45 minus 22 is going to be 23. So it comes out to be 9671.3 joules. Okay. Um, all right, so this is going to be the Q of the reaction. And obviously, if I rearrange the negative signs there, the negative gets down here. And now you need to find what the delta H going to be for this particular reaction. So the delta H is always going to be equal to the Q of the reaction divided by the moles of limiting reactant. Well, there's two reactants in this particular reaction. We got the HCl and we got the magnesium. And if you think about it, we have plenty of HCl in there. We used almost 100 milliliters of HCl. So there's a very good chance the limiting reactant is going to be the magnesium. So we need to figure out what the mole is going to be for the magnesium. So we're using 0.5 grams of magnesium, and obviously in your experiments you might very well be using a different amount there. And then go ahead and figure out the moles of that magnesium. So it's going to be 1 mole of magnesium divided by 24.3 grams of magnesium. So remember, when you're going from grams to moles, you're going to be using the molar mass or the atomic mass. Okay, so we got 0.5 divided by 24.3, so it's going to be 0.0206 moles. Okay, so once you have the moles of magnesium, after that should be a easy task to figure out the delta H, and let's call that delta H1 because that's what we have called it in the original reaction. So delta H1 is going to be negative 9671.3 joules divided by 0.0206 moles. So 9671.3 divided by 0.0206 moles, and that comes out to be 469,480 joules. And if I want to change that to maybe kilojoules, just because it's such a big number, I would say it's 469 kilojoules per mole. Now, this may very well be different than the actual value because I made up some of those numbers, but it's for the sake of how you do the calculation. So this is your delta H1 here. Okay, so then you have to figure out the delta H2 the same way for your second reaction, and that's what we're gonna do now. Okay, so your second reaction is gonna be the magnesium oxide and the HCl reaction. So assume I'm using about a gram of magnesium oxide. Okay, so 1 gram of magnesium oxide, and assume the amount of HCl is still going to be the same. So HCl is going to be 100 milliliters, which is roughly going to be 100 grams. And we're going to have a very similar setup where you got this HCl into this calorimetric cup, and you're going to be very well using the same calorimetric cup because you want to make sure if there is an error, it's going to be the same in both of those reactions. Okay, so you got this 100 milliliters of HCl, and then you add your magnesium oxide in there. So when you add the magnesium oxide in there, it's gonna be, in the beginning it might settle down here, but then eventually it's gonna start reacting with the HCl, and when it does react with HCl, it's gonna make magnesium chloride plus water. Okay, and we got to figure out what the delta H gonna be here. So it's actually going to be an exothermic reaction. So when this start reacting with the HCl, the temperature is going to rise up. And I forgot to kind of mention the temperature initially, but assume the initial temperature is the same as the previous reaction, is 22.0 degrees Celsius, because you're using the same, using the HCl from the same container. Okay, so once it's reacting, you're going to look at your thermometer, how high the temperature goes. And once the reaction is completed, you will have your final temperature. So assume your final temperature in this particular case is about 33.0 degrees Celsius. Okay, so it may very well be different in your actual experiment, but here I'm just picking some random numbers. Okay, so then we got to do the same thing we have done for reaction 1. So you may want to pause the session here and figure out what the Q and eventually the delta H going to be and see if it matches with my answer here. So I would say the heat lost by the reaction, okay, is going to be the heat gained by your reaction solution or the water, or I'll just say a reaction solution here. And I'm going to ignore the calorimeter here because what we said earlier, we're going to assume it's a perfect insulator where there's no transfer of the heat onto the cup and onto the surroundings. So it's going to be the mass of the solution times the specific heat capacity of the solution times the delta T. Okay, so specific heat capacity, we're going to be taking that as just the specific heat capacity of water. So the mass of the solution, well, we have 100 milliliters of this HCl, which means that would have been 100 grams. And if you want to be precise, you have added 1 grams of MgO, so that's going to be 101. Even if you use 100, it may not make any big difference in the calculation. So it's 101 grams times 4.184 joules over grams degree Celsius, and your delta T is going to be 33.0 minus 22.0 degrees Celsius. Okay, so now let's go ahead and do this math here. It's got 101 times 4.184 times 33 minus 22 is going to be 11. So it comes out to be 46.48 joules of energy that's going to be lost. So your Q of the reaction here is going to be minus 46.48. So minus just means it's an exothermic reaction. You're releasing the heat. Okay, so let's go ahead and figure out what the delta H is going to be now. So that's going to be called in a delta H2 because that's your second reaction. So it's going to be the Q of the reaction and divided by, in this case, what's going to be our limiting reactant? Well, it should be MgO because HCl is in an excess here. So your Q of the reaction is going to be minus 46.48 joules. And then, well, I don't know the moles of MgO. So let's go back and figure out the moles of MgO. We used about a gram of MgO. So 1 gram of MgO. And what's the molar mass of MgO? 1 mole of MgO. The molar mass of MgO, or magnesium oxide. Magnesium is about 24.3 and oxygen is about 16, so it's about 40.3 grams of MgO. So that way grams goes away, and that leaves you with 1 over 40.3. That's going to be 0.0248 moles. Okay, so let's go ahead and go back and plug that in there. So 0.0248 moles in the previous equation there. And now we're going to have 46.48.4 divided by 0.0248. And that comes out to be 187,000. So 187.435 joules over moles. And if I want to change that to, just probably write that down there. If I want to change that to kilojoules, so your delta H, and obviously it's a negative number, so don't forget that. It's going to be negative 187 kilojoules per mole. So that's the delta H2 you're going to be using in the second reaction. Okay, so now let's go back and we got the delta H's using the calorimetry, the specific heat capacity numbers, and doing these calculations. Now we're going to go back and just going to go ahead and write those down there. So we've got 469, so let's go back there. So your delta H1 is going to be 469 kilojoules per mole, and then your delta H2 is going to be 187 kilojoules per mole. Okay, so now my target reaction is magnesium plus oxygen making magnesium oxide, and everything else should cancel out. So if you look, I want to have, based on my target reaction, I want to have magnesium solid on the reactant. And in this case, magnesium solid in the first reaction you do have on the reactant. And this is the only reaction where you're getting the magnesium solid. So the first reaction, you don't want to do anything to it. You don't want to reverse it. You don't want to multiply with anything, with any number either. Now, the second reaction that I have in my target reaction is half oxygen, and when I go in my three reactions and see where that half oxygen is, it's going to be right there. And it's already on the reactant side, and it's already in half, so you don't need to flip it or you don't need to multiply it with anything. Okay, then your third reacting species, or actually the product in this case, is going to be the magnesium oxide solid. So your magnesium oxide solid in these three reactions is going to be in the second one right there. But the problem is it's in the reactant side. And since it's in the reactant side, I would have to make this go to the product side. So that means we need to flip this reaction. Okay, sorry about that. I forgot to write down negatives there. So both of those delta H's were negative to begin with. So don't forget that. So you need to flip this reaction. So when you flip this reaction, your delta H is also gonna flip the signs. So let me just kind of write down these reactions again so that we have all of them in one spot. So we got magnesium solid plus 2 HCl, and that goes on to make magnesium chloride plus H2, and delta H1 is going to be minus 469 kilojoules per mole. Okay, because we didn't do anything to this reaction, so we just left it as it is. The second reaction needs to be flipped, which means your products becomes reactants and your reactants becomes products. So I would have magnesium chloride plus H2O liquid, and that goes on to make magnesium oxide solid plus 2 HCl aqueous. If I'm going to go back and write down all these phases, okay, so then the delta H2 now, what's going to happen here? It's going to get flipped. It's not going to be minus 187, but instead it's going to be 187. So anytime you flip the reaction, your delta H's flips a sign. The third one, you want to leave that as it is. So you're going to have H2 plus half of the oxygen, and then it goes on to make H2O liquid. Okay, so then both of these reactants are going to be in the gas phase, and your delta H3 is going to be negative 286 kilojoules per mole. And then now we gotta add all these three reactions, but before we add them, make sure you cancel out anything that's common on both sides. So for example, if I start with the first reaction, this HCl, change the color there. So this HCl right there, we have two of those on the reactant side, and in the second reaction we have two of those on the product side, so they cancel out. Okay, all right, so let's look at another one. Then you have this MgCl2. The MgCl2 on the first reaction you have on the product side, which is only one of them, so I'll have that circled here. And I do have the MgCl2 on the reactant side on the second reaction, so that will cancel one another out. Okay, what else cancels out? And then uh, I got water. Let's look at hydrogen gas. I got hydrogen on the first reaction on the product side, which is this right there. And then I got the hydrogen on the third reaction on the reactant side right there. So they also cancel out. And then what else is there? The H2O liquid. So H2O liquid in the second reaction right there. And the H2O liquid on the third reaction and the product side, so they also cancel one another out. So a lot of these reactions and products cancels one another out. And now I don't see anything else canceled out, so let's just kind of write down what we are left out with. So we have magnesium solid plus half O2 gas, and on the product side you only have the magnesium oxide solid. Okay, so the only stuff that you have left out with is the magnesium solid, half of the oxygen, and the magnesium oxide there. Everything else cancels out. Now your delta H for this reaction is going to be the sum of all those three delta H's. So delta H1 plus delta H2 plus delta H3, and your delta H1 is minus 469, your delta H2 is 187, and your delta H3 is minus 286. So remember, your delta H3 was already given to you. You didn't have to do any experiments to find that. So I got negative 469 plus 187 minus 286, and it comes out to be minus 568 kilojoules per mole. Okay, so it seems like we have this reaction to be exothermic because the delta H comes out to be negative, and it makes sense. If you have seen magnesium burning, it produces a lot of energy. It burned with a very bright light. All right, so this is how you're going to be calculating the delta H formation for the magnesium oxide using the Hess's law and the calorimetry constant and the specific heat capacity. If you have any questions related to these calculations or any other questions that is similar to this particular problems, feel free to leave any comments in the section below.